Good morning, good morning. So, a common question that I see almost on a daily basis is, why do I need a resistor with an LED? What happens if I don't have one and plug it straight into my 5 volts? Well, I've got my trusty little box of assorted LEDs, every colour you can imagine, and I'm going to explore exactly what does happen if you don't have an LED. If you don't have a resistor with your LED. We'll all know what happens if you don't have an LED. Bugger all happens. Okay, first off, a little theory on LEDs and how they operate. First off, an LED is what's known as a non-linear component. Components like resistors are linear in that there is a linear relationship between the voltage and the current. As the voltage increases across a resistor, so the current increases directly in proportion. Now, with an LED, that is not the case. It is a non-linear. As the voltage across an LED increases, the current doesn't increase until it reaches the forward voltage of the LED, at which point it starts conducting and whoosh, the current goes off the scale. So you can see quite easily from this graph, if you were to provide, that's VF, if you were to provide 5 volts, what would the current be through the LED? If that's the normal, they're 20 milliamps that you'd normally want to have through an LED. What would the current be at 5 volts? Who knows? A rough estimate would be infinite. Except, of course, that can't actually happen. There's no such thing as a power supply that can provide an infinite amount of current. So you'll basically saturate the power supply and limit the current that can go to it. But that current will still be far too high. Okay, let's get an LED from my box. I choose red. A nice 5mm red LED. Okay, finding the forward voltage of an LED can be done straight off with a decent multimeter. They usually have a diode range. If I bring this up to the camera so you can see, we've got a little diode symbol on there. That should allow me to measure the forward voltage of the LED. Now, one thing to remember with LEDs is they are polarized components, so you have to find the positive and negative leads. Usually the flat edge of the LED, which is the shorter lead in this case, is the negative. So I shall connect a negative and positive. The LED lights up and we get 1.77 volts across there. So the forward voltage of this LED is around about 1.7 volts. That's at a very low current. I could work out the current, but I can't be bothered right now. We don't need to know. So this has a forward voltage of about 1.7 volts. That's the point where the curve on the graph starts to shoot up. So for proper operation of an LED, of this LED, we shouldn't provide any more than about 1.7 volts across it. And that's the critical thing. Also, you don't want to provide too much current. Now, the LED being a non-linear device will limit the voltage. Let's bring my power supply into play. I'm going to set the voltage to 5 volts. Okay. But the current limited to 20 millivolts. And I shall set this to voltage. Okay. So this has got 5 volts, but the power supply is limited to 20 millivolts. So, any guesses what will happen? 5 volts directly across this, but limited to 20 milliamps. It lights up perfectly. And the voltage across the power supply has been limited to 2 volts. At 20 milliamps, the forward voltage of this LED is 2 volts almost exactly. So regardless of what voltage you provide, as long as the current is limited, the voltage will be clamped by the LED to the correct voltage. Okay, I'm now going to do the same. This time I'm going to pump the voltage right up to 12 volts. Okay, but still limited to 20 milliamps. What's going to happen when I connect this? Is the LED going to blow? Or is it just going to light up like before? Here we go. Bang! That blew. Why did that blow? That blew because the power supply couldn't respond fast enough. So it got the full 12 volts across the LED with a full current load before the power supply could clamp down to the 2 volts that the LED needed. And you can see as well that the voltage across the LED is now 12 volts. So this LED with 12 volts straight across it, even though it's limited to 20 milliamps, has blown, and it's blown open circuit. There's no current conducting through because we've got the full 12 volts directly across the LED. One dead LED. Casualty number 1. Okay, what happens then? We know the forward voltage of one of these LEDs is about 1.7 to 2 volts. If I set my power supply to 1.9 volts, but 1 amp, what do you think is going to happen to this LED? We're allowing a huge amount of current through it, far, far more than the LED can cope with. But limited to 1.9 volts, which is at or just below the forward voltage at 20 milliamps. Okay. Ladies and gentlemen, place your bets, please. Oh, look, a nice gentle glow. 1.89 volts. And my power supply is reading about 4 milliamps. In fact, if I rearrange these pins and switch to milliamps, and this is connected. Have I got this the right way? No, this is backwards. Rearrange this the wrong way. Ow. Tip number 1. Don't clamp your finger with an alligator clip. Okay. 2.678 milliamps at a 1.9 volt input. So you can see that if you can provide the correct voltage, the exact forward voltage of the LED, you don't need a resistor because it is self-limiting. However, that's not a great way of doing it. It's a possible way of doing it, but it's not great. Any slight fluctuation in voltage, either the voltage of the power supply or the voltage of the LED, the voltage will actually change with temperature. As you can see on the screen there, the current is changing all the time as the voltage varies very slightly. It's not a steady constant value. I say the temperature does affect the voltage. The current affects the voltage affects the current. It's all interrelated. As the LED warms up, its forward voltage will vary slightly, which will change the current. And you risk getting a cascade effect, where eventually the current will just become too high for the LED and it'll go pop. Okay, so why a resistor? Very simply, to stop any of that happening. We need to provide about 2 volts to this LED. We have 5 volts and we have an unknown current limit, 1 amp. At 5 volts 1 amp, I shall feed this through my DMM at amps. Where's the flat side? There's the flat side. That's coming out of the DMM. That's going to ground. Okay, 5 volts, 1 amp. Oh, nice. Smoking. Overload on the ammeter. Let's switch that to full amps mode. We have smoke. Oh, that smells good. Let's bring this a bit closer, see if you can see a slight red glow going in it. And it's blown. Nice. That's what happens if you power your LED directly from 5 volts without any limit on the current. The 12 volt supply just blew it instantly. The 5 volt supply, it just got hotter and hotter and smoked and glowed. And that was quite beautiful, actually. There we go. Casualty number 2. Now, I didn't notice what the current was as it was going through there. That was limited to 1 amp, so it was probably going to be about 1 amp. So I'm going to do that again. That's fun. Don't want to hold the LED because that's going to get hot. Here we go. Yeah, 999 milliamps. Oh, that one blew a bit quicker. Nice one. Casualty number 3. So yes, without a resistor and with no limit on the current and the voltage not at the forward voltage, you get smokage. So why a resistor and how do you calculate the resistor? Why a resistor is to stop it from smoking. How to calculate a resistor? That is simple Ohm's law. Let's have a little circuit here. There's our resistor. There's our LED. There's our power. We've got 5 volts, a resistor, and we know the forward voltage of the LED is around about 2 volts. We'll use nice round numbers to keep things easy. We need to make sure that the voltage across the LED is 2 volts, but the voltage across the power supply remains at 5 volts. So the resistor is used to drop the extra 3 volts, which is 5 volts minus 2 volts, so that you get a nice balance. 3 volts plus 2 volts adds up to the 5 volts of the power supply. So we know that with Ohm's law, I equals V over R. A very handy thing to have around is what's known as the Ohm's law wheel. Let's just get my tablet and bring one up for you. Right, so you've got your resistance, your current, and your voltage all form basically a triangle. If you know the volts and you know the current, you can calculate the resistance. If you know the resistance and the current, you can calculate the voltage. And these are all the formulae for doing that with. In addition, you've also got a power calculation for how much power will be dissipated by a resistor. So we know from this that the current through a resistor is equal to the voltage across it divided by the resistance. So we want a current of 20 milliamps for this LED. We know that that's a decent current at its forward voltage. So 0.02, and we've got 3 volts across the resistor divided by R. So we rearrange that, or just quickly reference our Ohm's Law wheel. We want the resistance, voltage divided by current, 3 divided by 0.02, 3 divided by 0.02, 150 ohms. There we go. So if we have a resistance of 150 ohms, with 20 milliamps flowing through, that will drop 3 volts. But because we've got the fixed voltage of the LED, the resistor will drop 3 volts regardless. So 150 ohms with 3 volts across it will allow 20 milliamps to flow through it. And that's basically the theory of it.